Hello, my name is Adalberto and today I will be talking about machine learning based lighting dimming control. The content of the talk starts from the why are we doing this, how can we achieve it, and what's the final solution that we are proposing. Then we're going to dive into the control workflow, talk about the challenges that you have when you're just estimating daylighting, the machine learning model pre-training methodology, how to estimate the dimming values, and final remarks. So, why? Lighting uses about 10% of total energy used in commercial buildings. This plot is for the US, but around the world is around this percentage and sometimes can be much higher, up to 40%, depending on the building. Then the potential of saving energy by using dimming technologies ranges from 40 to 70% depending the weather conditions. That's a very important potential savings that can be achieved. Also, daylight sensors are not easily available in buildings. They are usually in buildings with a lot of technology, but they also sometimes are not very well calibrated. So yeah, there are some issues when we're talking about daylight sensors in typical commercial buildings. Then, how do we want to solve this issue? First, of course, we want to modulate the light to take full advantage of natural daylight. Daylight is not only free, but it's also the best type of lighting source or lighting that humans can use for doing their everyday tasks. To achieve this, we also need a low latency workflow, so we don't want to spend a lot of energy and a lot of time calculating the current dimming position, because that also takes energy and then also can create a weird user experience. By taking advantage of the dimming capabilities of some buildings, so if the building is connected to a proper platform which can interact with the dimming system, then this is part of the solution. And finally, we use easy to install sense modules, which are wireless lock sensors that measure something we call vertical outside illuminance. In the picture you can see an example of a sense module. And what? Well, this is the machine learning based lighting dimming control service that we are developing here. So let's talk about the control workflow. So this workflow will occur every time a dimming modulation calculation is required. There's a few steps, but we're gonna go through the most important ones. The lighting parameters, that is the required information that is needed from the building at any given time when a calculation is required. That includes the information whether the room is occupied, if there are blinds that are controlled or controllable, then we will need to know the position of such blinds. Additionally, we want to calculate or to know the vertical outside illuminance. This data will come from the sense modules we just talked about. And we want to know if the lighting in that room has any override status. What does that mean? That sometimes, for example, the user doesn't want their lights to be automatically dimmed. For example, during a presentation where the user wants to keep the lights completely switched off. Once we have that information, which typically will come from a digital twin, then it is possible then to call the Azure machine learning endpoint per project, and then pass all the requests for prediction for each of the lighting groups that we want to control. Why we are using machine learning is because it allows low latency control, and we will see how this compared with other traditional alternatives, and that machine learning models some of them can be retrained, so they don't forget the initial data set or the initial data that has been used for training, but new data can improve the subsequent simulation predictions or predictions of the model. This is a great advantage of machine learning models. And finally, the calculation for the new dimming, it's using a very simple rule-based algorithms that calculates how much dimming do you need based on a lux deficit or dimming deficit. We're going to talk about this later. So let's talk a bit more about daylighting estimation. So there are multiple ways of estimating daylighting. The most common one is the one used using simulation engines. Simulation engines use only the physics principles and use something called ray tracing typically to estimate the light or the natural light in any surface. In our case, we are interested on the surface at the work plane height, so in your desk, for example. However, traditional simulation engines, they are not designed to simulate partially closed or partially open blinds. Then, through research here, we have tested what's the performance of these simulation engines if we want to discretize such blinds. That means to represent the different positions of the blinds. That was resulting on 1 to 5 minutes, which was a lot of time. Then, thanks to the collaboration with the University of Eindhoven, we have been working on a lightweight simulation engine that manages to do the same, to get the same results, but using only 3 to 20 seconds. That's already a big improvement, and kudos to the TU team for this. But in practice, if you want to achieve near real-time control, that's still an important latency. So the next step is to take those results from the lightweight simulation and then combine them together into a machine learning model that then can create predictions in less than 30 to 200 milliseconds. So once that we agree that we want to use a machine learning model, what we want to do is to use the simulation results, the lightweight simulation results, to pre-train the model. To pre-train the model, what we do is to run 1 year simulation. So that's a year hourly simulation, which in total is something on the lines of 8,760 simulation time steps for the entire year, which is the number of hours. For that, at each hour, we record the altitude of the sun, the azimuth of the sun. We take the vertical illuminance at each time step, vertical illuminance in all the windows, or they are called apertures in the simulation environment. The blind positions, so for every time step, we have a random blind position generator, so we can simulate many combinations of blind positions throughout the year. And finally, we keep track of the values in the sensors over here. Let me point them here. So the illuminance, wherever we need them, which in our case is at the desks, wherever are desks. So we want this illuminance ultimately as our output. And then we group them. We typically decide to group them because typically you want to get an average of certain points in the same regions of the room. So that creates what we call a simulation data set, which consists of such information per like solar altitude, solar azimuth, vertical illuminance in the north, vertical illuminance in the east, vertical illuminance in the south, and so on, and the blind positions from 0 to 100. That data set then has around 4,000 points after 1 year of simulation. That 1 year simulation will take 2 to 3 hours, and we keep around 4,000 points. That is because it's just the time when the sun has a altitude higher than 0. That means during the daytime. In parallel, we create a validation data set. The validation data set is the same data inputs, but they are taken in a specific point in time in the building. So that is, we take the illuminance and we take an average of the illuminance in the target area that we want to validate against. For example, in this area, in this desk, yeah. And then by exploiting the capabilities of a digital twin, then we can easily create the entire data set because the digital twin knows about the blind positions, knows about the different vertical illuminances, which is data that is coming from the sense modules. So we have the simulation data set. That simulation data set with 4,000 points is used for train a model, what we call a pre-trained machine learning model. And then once it has been trained, we can take the validation data set, show it the inputs, wait for a prediction, compare with the measured values, and then get an estimation of the error. If that error is less than what we can tolerate, then we say that the model is ready for deployment. If not, then data needs to be collected, creating a retraining data set, and then this data set is used for retraining the machine learning model. As I mentioned, some machine learning models allows retraining or further training, which means that it keeps memory of the previous data set that has been trained on, but then uses the retraining data set for fine-tuning the predictions. This is trying to combine the strengths of simulation, but then doing this final calibration with real measured data. This process can be repeated a number of times. We have done something on the lines of 2 to 4 cycles until we get a error that is deemed as acceptable. So once that's done, the machine learning model is deployed, and then we have what we call an endpoint or a service that allows us to then predict the daylighting for any group and any floor in any building. Finally, we want to talk about how do we do the calculation in near real time. So every time there is a demand for dimming modulation, the first step is that daylighting is estimated. So as we spoke, we estimate this prediction target, and then we get the average of this part given a blind position, and this assumes, of course, that the light is 0%. This is very important, right? So the daylighting already is ignoring the impact of artificial daylighting, which is something that it's difficult to do otherwise. Once the daylighting is estimated, it is compared to the target lux for a given space. For offices in general is 500 lux. So that is, if the prediction of daylighting is around 300, and then the goal is 500, then you have a lux deficit of 200 lux. Those lux that are missing, let's say the 200 lux, are then converted to a luminous flux. So from here, 200 lux are needed. Then there is a formula that uses the distance between this, the target area and the source, and then it is possible to convert into luminous flux. So those 200 then are converted to a number of luminous flux. And finally, it is possible, and this will depend on the type of vendor and on the type of technology of the lamp, it is possible to estimate the relationship between the luminous flux and the current. For example, if you need 200 lux that then are converted into lumens, for example 600, then there will be a relationship here between the amount of current that you need to achieve that. That sometimes it's then converted to power output, but that will depend on specific lamps. With that information, then it is possible to have an estimation of what's the right dimming percentage for that to meet those 200 luxes. This process takes around 200 to 500 milliseconds per space. So this is quite important to keep it very, very quick, very, very low, with very low latency, meaning that it is possible then to estimate any number of lighting controller groups, because this process is highly scalable thanks to the certain properties for machine learning model prediction infrastructure. And that's it. So we're going to talk about just a bit of the final remarks. This process is very scalable, as I mentioned. It takes about the same time to calculate 1 or 100 what we call lighting groups, and that's because that's one of the benefits of using machine learning models. And the process is flexible. That is that it is possible to deploy any number of virtual sensors and then group them, and then you can really have a lot of control as to how do you want to control the different lights, groups of lights between your building. So you can have multiple groups and then really take advantage of the lightings that are close to the windows, and then have a different group for the lights that are further further away from the blinds. So it's very flexible. It is easy to fine-tune. If you have a digital twin, then you can collect samples, and the process might need some planning. For example, as I mentioned, it might need some data collection in summer, some data collection in winter, so you have the two extreme conditions, and you expect that because of the combination of simulated data in the machine learning model, then the machine learning model should be able to interpolate or to correct anything in between. It uses data inputs from the easy to install sense modules. Those are the sense modules that are wireless. They can be installed, a few of them per orientation, and then combining with the blind positions from your building, then it is possible then to have a continuous service for daylighting, which is the solution that we are developing here. Thank you very much.